In this video, we will learn about resonance structures and drawing curved arrows. You have seen that bond-line structures are quite efficient and is the preferred way for organic chemists to draw the structures of compounds. However, they do have one shortcoming, which is usually fine, except when you're trying to depict something called a resonance hybrid. For example, if we drew this molecule with a double bond, we can see that the pi electrons sit between the two central carbon atoms, which is perfectly fine. However, when we use the bond-line structure to depict this allylic compound, it gives an incomplete picture of this compound. It simply states that the pi electron are fixed between these two central carbon atoms, but it turns out not to be the case. So let's visit this structure. Remember that the double bonds mean that the two carbon are sp2 hybridized, and that the positively charged carbon at the end, the carbocation, is also sp2 hybridized with an empty p orbital. So if we were to draw the orbitals, we see that the pi electrons are in the p orbitals of the two central carbons, but there is also this empty p orbital that's perfectly aligned right next door. This creates a continuous system of p orbitals. A perfect overlap of p orbitals occur where the pi electrons can be delocalized, can be moved around in this system. The farthest carbon on the right was once an empty p orbital, a positively charged carbon. Now with the pi electrons transferring over, the carbon on the left now, the original central carbon, is now the empty p orbital, the site of positive charge. So we can say that the pi electrons are associated with all three carbons. And this is where the static bond line structure fails us. It fails to represent the delocalized nature of that pi electron into the allylic carbon. And so we need two bond line structures to represent the reality of this compound, where the positive charge is between two carbon atoms. To represent this, we draw the resonance structure with a straight two-headed arrow within brackets. This is what we call the resonance hybrid or the resonance structure. And this spreading out of electrons is called delocalization, which is a stabilizing factor. Remember that neither of these structures represent the true reality of the compound, but a hybrid of the two. And I want to especially note to not think about this as these two structures are interconverting between one another. One moment with a structure on the left and one moment with a structure on the right. But at all times, it is both of these structures at the same time. And as you can see how difficult that is to present that with the static bond line structure. We will use curved arrows to represent resonance structures. And later on in the semester, we will also use curved arrows to draw mechanisms. So first, let's get down to some fundamentals. Make sure when you draw curved arrows that it is indeed curved. This is a straight arrow, which usually represents the direction of a reaction. When you draw a curved arrow, it is similar in that it has a tail and an arrowhead, but make sure that the arrow itself is curved. When we use curved arrows to draw resonance structures, make sure that you understand that it does not represent the movement of electrons, although it will eventually represent actual movements of electrons when we draw mechanisms later on. But when we draw it for resonance structures, we are simply using it as a tool to move electrons around even though they are not moving around. So this quote-unquote movement of electrons is depicted where the tail represents where the electrons are coming from and the arrowhead represents where the electrons are going. And so for now, we're just going to focus back on drawing curved arrows for resonance structures. And to do this, there are two simple rules you must follow. The first is to not break sigma bonds. And this rule is because when you break a sigma bond, you're essentially making two molecules where you start out with one molecule. And since resonance structures are trying to represent the reality of one single molecule, if you break a sigma bond, you are introducing new molecules into your structures. And the second rule is to not exceed the octet. And this is really only important for carbon, nitrogen, and oxygen, elements of the second row. Remember, the key word here is to not exceed the octet. If you are under, that is permissible. So let's go over some examples. We started this discussion with the double bond allylic compound. Let's see how would you draw the curved arrows for that resonance structure. So remember to visualize that we are pushing electrons around. So in that example, the pi bond between the two central carbon atoms, highlighted in red, are moved towards the allylic carbon, making the new double bond and leaving that first red carbon positively charged. Notice that we did not break either of the rules. No sigma bonds were broken, and we did not exceed an octet. But we did notice that we created a carbocation which has less than 8 electrons, which is permissible. Let's do another example. Let's see if this breaks any of those rules. In this example, we took the pi electrons and pushed it towards the oxygen, dumping the 2 electrons onto the oxygen itself, leaving behind a carbon that is deficient in electrons, so it is positively charged. I forgot to put in the positive formal charge for oxygen, and we know why it has that formal charge already from previous discussions. But the point I want to make here is that when you draw resonance structures, the overall charge of one structure should equal the overall charge of the other. So in this case, if I drew in my right-hand structure with one positive charge, so overall that whole molecule is a positive 1, then my original molecule on the left should also be a positive 1 charge. Remember, when we're drawing resonance structure, we're drawing structures that represent the same identical molecule. So if one is plus 1 charged overall, then the other one must also be plus 1 charged overall. Let's continue with some more examples. How about this molecule? Can I draw this arrow, right? So let's take a look at this. We shifted a sigma bond between 2 carbons and dumped it onto another carbon-carbon bond, making it a double bond. That positive charge now is gone, but then it leaves a positive charge on the other carbon. Is this allowed? This is not permitted, right? Because it breaks a sigma bond. And when you break that sigma bond, you have created 2 totally new molecules. So this is not a proper curved arrow, so therefore these are not resonance structures. Let's try another one here. Can I push these electrons down? Does this work? So seemingly it doesn't break any rules, right? But remember, when we use bond line structures, you have to be careful of those hidden hydrogens. Remember that this carbon is lacking one more bond to be tetravalent, so it's missing that hydrogen. When you draw the resonance structures, that hydrogen is still there. So now with this knowledge that there's a hydrogen there, what's wrong with this structure? That carbon exceeded the octet, right? It has 5 bonds, so 10 electrons, so that's not good. So this also is not the proper curved arrows, so therefore these are not resonance structures. To contrast that, what if we had a different molecule where we had this carbon as a carbocation instead? Will this have a resonance structure? Are those curved arrows allowed? Yes, they are, right? Because you did not break any sigma bonds and you did not exceed the octet. So this is perfectly fine. You will be drawing a lot of resonance structures in this class, and one way to be proficient at doing so is not only to practice a lot, but also to be able to recognize common patterns of arrow pushing when it comes to resonance structures. There are only 5 curved arrows that you can draw for resonance structures. If you draw anything different from these 5, you're likely drawing a wrong curved arrow and therefore wrong resonance structure. And so let's go through these one at a time. The first pattern is to recognize when you have an allylic lone pair. First, let's determine what is allylic. When you have a carbon-carbon double bond, the carbons that are involved in that double bond is called vinylic, and the position that is attached to that vinylic carbon is called the allylic position. Let's see if we can identify the allylic position in this molecule. We have here our double bond and the vinylic carbons, so the atoms highlighted in green are considered the allylic position. Therefore, the lone pair on that nitrogen is considered an allylic lone pair. This nitrogen on the top is too far away, so its lone pair is not considered an allylic lone pair. Let's take a look at how we can draw the curved arrows for the allylic lone pair. First, convince yourself that these lone pairs are indeed allylic. In your first arrow, the lone pair of the allylic position is pushed to become a pi bond. Remember that carbon is tetravalent and has that hydrogen there. So when you make a double bond to it, now it would have 5 bonds. So that's not possible. In order to alleviate that, we are going to draw a second arrow, this time breaking the existing pi bond, the double bond, and pushing it towards the single carbon, creating a lone pair. Notice that you are essentially pushing the negative charge around in this pi system. It started out being located on the farthest right carbon. Now it's going to end up where your last arrowhead is pointed at. Now let's take a look at the second example. Can you locate where the allylic lone pair is? Since this is our pi bond, then our allylic lone pair is up here on the oxygen on top. So in the same way, let's draw the curved arrow. Starting from the allylic lone pair, pushing towards that pi bond. So you are going to make a lone pair become a bonding pair. Once you make that bonding pair between that oxygen and carbon, then that carbon has too many bonds. Let me draw what I mean by that. If you push the lone pair down to make that double bond, this carbon in the center has now 5 bonds, which is not allowed. To avoid that, we need a second arrow. The second arrow is the arrow that breaks that double bond, pushing it towards the oxygen atom. Let's pause here to do a compare and contrast between these two resonance structures of the same pattern. In the first case, we noticed that we started out with a negative charge, and we're shifting that negative charge around. So overall, this molecule still has that one negative charge. In our second case, if we started out with 0 charges, after we draw the resonance structure, we have created a positive charge and a negative charge. But the net charge is 0, which is what should happen since our molecule on the left is also neutral. And let's see one more example. Can you locate where the allylic lone pair is? Right, so this is your pi bond. So allylic to it would be the lone pair on the nitrogen. So as before, we're going to push the allylic lone pair towards the pi bond and breaking the pi bond with a second arrow. And lastly, as a side note, maybe some of you have caught this, the last two examples that we did technically do not have vinylic positions because they don't have a carbon-carbon double bond. They have a carbon-oxygen double bond. However, it is similar enough that we still can consider the lone pairs one bond removed away to be considered the allylic position and having the same arrow pushing patterns. Before we go on to our next pattern, I want to go over a peculiar case. It is the case of pyridine. This ring structure with a conjugated pi system and a nitrogen with a lone pair. And this lone pair is allylic to a pi bond, so you might be tempted to draw a resonance structure from it. However, this resonance structure is not valid, and the reason is due to geometry. Remember, to have resonance, you must have overlapping orbitals in order to spread out those electrons. That lone pair on a nitrogen, due to geometry, cannot overlap with the neighboring p orbitals. Let's take a look at that in more detail. Alright, so we have here this pyridine. Can you determine which orbital holds this lone pair? Recall that this nitrogen atom has steric number of 3, so its orbitals are sp2 hybridized, one orbital here, one here, and one here. So that last sp2 orbital is what holds the lone pair. Let's take a look at those orbitals in detail here. Because of the conjugate pi system, we can see that there are p orbitals in all of the atoms in this ring structure. And all the p orbitals line up pretty quite well. They have a perfect overlap, so the electron density is actually shared between all these atoms. So you can draw a resonance structure with the aromatic pattern that we'll discuss later. But you cannot draw the allylic pattern because this lone pair is orthogonal to this pi system. So they do not overlap well enough to be able to resonate. So because of that, there's this particular term we want to introduce at this point. We say that because that lone pair cannot participate in resonance, it is stuck on that nitrogen, so it is localized. This is in contrast to the lone pairs on nitrogen on a previous example where it was able to spread out. Because those lone pairs can have resonance structures, it can spread out. It is not stuck on that nitrogen solely. We call it delocalized. So just make sure before you draw a resonance structure with a allylic lone pair that those lone pairs can indeed be delocalized. Okay, so now let's move on to our next pattern. In our first pattern, at the allylic position, we saw a lone pair, which is considered a region of high electron density. So we're trying to spread the electron density around, and therefore spreading that negative charge around. In this case, instead of having a lone pair, what if you had a carbocation? So it is still within that pi system so that the electrons can be spread around. So in this case, the direction of the electron flow is in reverse. It's going to flow towards the allylic position. The pi electrons will flow towards the carbocation. And when you do that, you leave an electron hole, a carbocation, on the other end. In this curved arrow pattern, you only need one curved arrow. Later on, we will see this being used in a conjugated pi system. The word conjugated here is when you have multiple pi systems that are separated by a sigma bond. When you have an allylic carbocation in a conjugated pi system, you can have multiple resonance structures. You can obtain each resonance structures with one arrow at a time. Let's first move that first pi bond towards the carbocation, creating our new pi bond and our new carbocation. Notice that this new carbocation is now allylic to the other pi system. So we can again draw another curved arrow for this resonance, pushing the pi electrons towards the carbocation, creating a new pi bond and a new carbocation position. So these are the three resonance structures that can be drawn for this molecule. Notice that we can obtain all three resonance structures if you only push one arrow at a time. Our third pattern occurs when you have a lone pair that is adjacent to a carbocation. Unlike a lone pair that is adjacent to a pi system, you only need to have one curved arrow for this resonance structure. Again, we're trying to spread the electrons around. So the lone pairs will be pushed towards the carbocation, forming a double bond. Since that carbocation can accommodate one more bond, it does not need to break any bonds, unlike the case in our first pattern, the allylic lone pair. Let's see that again. Allylic lone pair here, push towards the carbocation, giving us this double bond between the carbon and the nitrogen. Notice again that you start out with a positive charge on the left, so your resonance structure on the right would also have a positive charge overall. Our fourth pattern of curved arrows for resonance is when you have a pi bond between two different atoms, as seen here in this carbonyl. And when you have this situation, you want to always draw it so that you break the pi bond and giving the electrons towards the more electronegative atoms, which makes sense because it is more greedy for electrons. So one arrow is needed for this pattern. Again, keeping in check your FOMO charge, the oxygen now is negatively charged and the carbon is positively charged. Did you notice that this pattern is basically the reverse of pattern number 3? For example, if we go up to our second example in pattern number 3 here, we see a double bond between the carbon and the nitrogen. So in order to draw a resonance structure from this, you want to draw the breaking of the pi bond and movement of the electrons towards nitrogen, which basically gives us our first resonance structure. Our last pattern is when you have aromatic pi bonds. And this pattern is essentially the conjugated system we talked about earlier, where you have pi bonds that are removed from each other by one sigma bond. In this case, though, you have a ring structure constraint to it. In this case, you will draw multiple curved arrows at the same time. The breaking of all the pi bonds and making of new pi bonds at the same time. Now, just because you can draw the resonance structure, it does not mean that structure is significant. A structure can be a major contributing factor, a minor contributing factor, or totally insignificant to the true reality of that molecule. In this section, we will follow some simple guidelines to help us determine if a structure is significant or not. So let's go over some rules that will help us assess the relative importance of a resonance structure. And the first rule is that the most significant contributor will be the one that have the most filled octets. So let's take a look at an example. Let's say you have this molecule, and then we can draw a resonance structure for it. Both of these structures are valid structures. However, they are not of equal significance. The first structure that we drew has a carbocation, so it lacks an octet. In the second structure that we drew, all the atoms have a filled octet, so that will be our major contributor. Anytime you are comparing two resonance structures and one lacks the octet, then that one will be the minor contributor. Let's take a look at another example. Let's draw in the curved arrows to see what kind of resonance structures this molecule has. And from the second structure, we can continue to draw resonance structure because we can see that there's a positive charge allelic to that pi bond. So now we have three resonance structures. So how do you want to analyze our situation here? In our first structure, we see that every atom that needs an octet has an octet. So that looks good. In our second structure, we see that there's a carbocation, so there's a lack of octet. So we already know the first structure is better than the second structure. What about our last structure here? In our last structure, we don't have that carbocation anymore, so that carbon has an octet. However, now the oxygen on the bottom lacks the octet. When a carbon lacks an octet, that's okay, but if an oxygen lacks an octet, that's not allowed ever. Even between these two structures, both lacking octets, the structure on the right will be considered insignificant. Okay? Now going back to the two that we have left over, we said the first structure has a full octet, so therefore automatically that's going to be our major contributor. And our carbocation structure is our minor contributor. Alright, so that first rule is the most important rule you want to follow. Now if there's a tie and we need a tiebreaker, there's this second rule. And our second rule is that the structure with the fewer formal charges is the one that is more significant. So let's take a look at an example. So in this molecule, again, we see that there is an allylic lone pair, so we can draw a resonance structure from that. And from our middle structure, we can draw another resonance structure because we see a double bond between two different atoms, the nitrogen and the oxygen. All right, so let's analyze these three structures. The first structure that we drew has all octets, so that's good. The second structure that we drew also has all octets, but has the charges. And in our last structure, we have a carbocation. Okay, so automatically, the last structure will be your minor product because of the first rule that we talked about. Now let's go back to the first two structures. They both have octets for atoms that need the octet, so they are considered both major contributors, but one will be a little bit more important than the other. So it turns out we can use rule number 2 to break this tie, and rule number 2 says a structure with the fewer formal charges is the more significant. So the first structure has 0 formal charges, whereas the second structure has a positive and a negative formal charge. So our first structure is considered the most significant contributor. So in this example, we start out with a molecule that is neutral. So let's see an example of a molecule that has a formal charge to start out with. So let's take a look at this molecule here. We can see there are multiple patterns we can draw. We can draw it as an allylic lone pair, or we can see that the carbon-oxygen is a double bond between two different atoms where oxygen is more electronegative. So we can draw an arrow like this, and giving us this structure here, from which we can draw another resonance structure. We see a lone pair adjacent to a positive charge, right, giving us our last structure here. Now notice that you started out with one negative charge, and then in the middle structure you've created 3 charges, 2 negatives and 1 positive, which is a net of negative charge, so that's legitimate. However, because you've created so many new charges, that structure is very unlikely, so it's going to be your insignificant structure. And so we have 2 left, the one on the left and the one on the right. Both these structures have only 1 negative charge. So how do we break this tie? So here comes rule number 3, which states that if all things are equal, the negative charge should be on the more electronegative atom, which makes sense, right? It's electronegative, so it wants more of that electrons. In our first structure, the negative charge is on the carbon. And in our second structure, the negative charge is on the oxygen. Oxygen is a more electronegative atom, so the structure with a negative charge on the oxygen will be our major contributor, whereas the structure with a negative charge on the carbon will be our minor contributor. Now this rule also works if you have a positive charge. So if all things are being equal, the positive charge should be on the less electronegative atom. Just like in this example here, the structure on the right will have a positive charge on a less electronegative atom, so this would be our major contributor. And the structure on the left has a positive charge on a more electronegative atom, so that's not what we want. So that's going to be considered the minor contributor. All right, so this wraps up our discussion on resonance structure.